All right, this is a flea market find. Actually, it was a garage sale find, maybe an estate sale find. A friend of mine was at an estate sale a few months ago, and the guy had some old, pretty vintage ham radios. Nothing that I really wanted. I was kind of tempted, and he had a Kenwood Trio. I've got other radios that receive just fine, so I don't know. I didn't really need anything, but this caught my eye. It was kind of tucked away, and I said, what kind of price tag does the guy have on this? And he goes, no price tag, why don't you make an offer? So I said, 20 bucks. So he asked the guy 20 bucks, and the guy says, yeah, sure. Because it looks, you know, it's definitely homemade. It's kind of crusty, a little bit. But I knew what was inside. At least I thought I knew what was inside. So I said, yeah, 20 bucks is a steal. I especially like the meter. The meter is really strange. It's a Weston meter, and it's a dual needle SWR, so forward power and reflected power. And instead of the reflected power going down, it's up. So yeah, so that's kind of interesting. So I don't know what kind of circuitry is driving this meter. That'll be interesting to see. And then I assume that this was a roller inductor and a capacitor and another capacitor. Like I said, it was several months ago. The guy bought it, and it's been in his garage. He recently changed locations where he works, so he's close to my house now. So we met up for lunch, and I finally gave him the 20 bucks and got my fancy box. So you'll be seeing it for the first time as I'll be seeing it. So I noticed right away that there's no screws on the top cover. That's not a good sign. Definitely not a good sign. So we'll pop that off, and we will take a look inside. Definitely a nice big roller inductor. Let me pop something up at the back here so it doesn't fall over. So huge meter. This meter is just lovely. It looks like a military. It looks really nice. There is a little box back here. So what it looks like is he's taken a SWR meter and chopped it up and popped it in here. So the directional coupler has been stolen out of another meter and put to use here. This is not an inductor or a capacitor. It is a resistor. So it must be for zeroing out the dual needle meter to zero it to measure correctly in SWR. What else do we have? We have a nice big variable capacitor here. It looks like it's out of an old radio, but this is really what I'm interested in here. So very nice roller inductor, and it has a weird switch here. So it switches between what does it switch between? Switches between the input. I assume this is the input going to the capacitor, and ground's on the other side. I don't know. Looks like it's either switching it to the inductor or to the capacitor. That's kind of a weird thing. So we'll have to figure out how this thing is wired. But it certainly looks interesting inside. Let me zoom you in a bit so you can get a better look here. Alright, see what we can find out more about this thing. Alright, I just ripped the cover off, didn't even look, but the schematic is in the cover. I always say that you should do this. And the guy did it. He actually drew it on the cover, not taped in something, but actually drew it on the cover. So it looks as though we have an L matching network. but it looks like it's able to switch to have the capacitance in front or the capacitance in the rear. So if you are greater than 50 ohms, you have it in one location, and if you're less than 50 ohms, you have it in the other location. I don't remember which is which. It says that the capacitor here is 450 microfarads, or is that picofarads? That's probably picofarads, duh. And I don't know what the inductor goes, but we'll measure those two things. And then over here, it has a picture of the actual bridge. So it says there's a red wire, a black wire, and a white wire. Then here's the bridge, the 4 resistors. Looks like each one is tunable, so that's kind of nice. You can set each one to 50 ohms, I guess. And then here's the meter. And then there's a switch on the meter, which is kind of weird. You can basically make it work or not make it work. It looks like. I don't know why you would have a switch there. I have to think about that, but that doesn't make any sense to me. And I don't know which resistor is on the front. Now, the way that it's wired up, it would seem as though it's 2 potentiometers that work together. So maybe it's these two that work together. That might make sense. I don't know. I'll have to sort that out some more. But it's not a T network. Certainly could turn it into a T network by adding another capacitor. But L networks work fine too. Yeah. So I think the next thing to do. Oh, and then there's one last thing. So in remembrance of Silent Key, I think this was probably from his estate, unless he bought this from somebody else, is W6RRN Clarence Vermache or something like that. W6RRN 73. So let's take a look at what we can find out inside this thing. Alright, so it looks like he did some fiddling here. This wire comes down, and it looks like it's soldered to each one of these capacitors. So these are individual capacitors. They come out to individual lugs here. And it looks like he soldered it like off and on. I'll put these two together. No, I'll add this one. No, I'll put it here. No. And what he's done is these solder connections are actually broken. I don't know if something let loose in here, but you can see it actually snapped. And it doesn't look like it was desoldered. It looked like it was a mechanical fracture. And so only this capacitor is connected right now. These two other capacitors are not connected. So we can measure these. Let's see here. Put that one here. Let's put this one here on this capacitor, since that's where it's connected. And alright, let me let you see what's going on here. I've got a LCR meter, so it's 523 picofarads on that end capacitor. On the next capacitor, it is, let's see if I can do this without shorting to anything else. So all of the interleaving blades are at maximum, so it's the biggest capacitor it could be. So this one's 525, about the same, and the end one over here is 600, so a little bit more. But certainly all of them are not connected, although they look like they were at one time. I think if it's 500, 500, 500, that's quite a bit of adjustment. I think 500 is enough for the hand bands, but I'm not quite sure. Some people put in a switch where you can either gang them together or not gang them together if you want to have a little bit more variability. So I'll take a look at that and see how we want to wire it up. Looks like it just has some 12 gauge wire here. And then we have a roller inductor, so let's see if we can figure out how to measure that one. Alright, I've decided this box needs a complete rewiring. It wasn't done all that good in the beginning. We saw some cracked solder joints, and all the solder joints look a bit cold. Looks like he wasn't good at soldering. His mechanical skills are pretty bad putting the box together, so time to redo this whole thing. We do have a very nice roller inductor. I suspect it's military surplus from World War II, maybe. It has a nice roller follower here. You connect one to one of these lugs, which in turn grabs the inductor, and then this grabs the roller. It also has a nice little spinny knob here, so you can go fast. Let me zoom down here a bit. Go off the screen. And it has a locking knob, so it won't go anywhere. It also has a reduced counter here, it goes down all the way to one end, and it should be at 0. So 0 is going to be here. So when we finally bottom out, we see that we're at 0. And it goes up to, I think, 35. So 35 turns, or 35 marks on here. I don't know how many turns. I haven't calculated it. Maybe there's 35 turns on the thing here. But anyway, we have a very, very nice roller inductor. So I'll clean that up, and I've already cleaned it up a little bit with some alcohol and some contact cleaner, but it needs more. And then we have the inductor. I've gone ahead and shorted all 3 outputs, so these 3 capacitors are all ganged together, so it'll give us the maximum amount of capacitance. And let's see. Well, we can actually measure things here. Let's measure the capacitor. I'll measure it. Open. And I think you can see that. Let me bring it over here a little closer. And we are at 39 puff. And if I totally engage the thing, we're at 1527 puff. And halfway, it's about halfway, we're at 558 picofarads. So very nice range. And the inductor, I'll do a quick measurement on it. We're at one end of the inductor right now, over here. And so let's go halfway. Halfway we're at, let's see here, 12 microhenries, and at the other end we're at 25 microhenries. So 0 to 25 microhenries and 0 to 1500 picofarads, something like that. Alright, so I'll go ahead and look up stuff and figure out what type of transmatch we can make out of these things, and whether we want to add a second capacitor and make it into a T-network and stuff. I'll go kind of sort that through. But I thought, I've never had a roller inductor before, and I thought, geez, we can really do some clever things here. Let me move this out of the way, and move this out of the way, and let me talk a bit about Smith charts. Now, I'm not going to teach you Smith charts. They're very complicated. I actually went to a class once on learning matching networks and Smith charts and everything, but that was back in 1985, so I don't remember that much of it. Let me rearrange the camera here, and let's talk about Smith charts. All right, so the Smith chart that's on the little NANOVNA doesn't have all of these lines, but these lines are very nice. There's actually 2 sets. There's blue lines and there's red lines. And the red lines are kind of circles that come this way, and the blue lines are circles that come this way. And let's go ahead and use a magic marker here so you can see things. And we know that we can arbitrarily choose what we want in the center. So our VNA calibrates at 50 ohms. So 50 ohms is going to be our point right here in the center. Okay? And then I've kind of mentioned before, if we go in this direction, it's plus Z, which also means inductance. And if we go down, it's minus Z, which is capacitance. So if we have a circuit and we add a parallel inductor or a parallel capacitor, we will move either up or down. But do we go straight up or straight down? No, we follow these lines. Okay? So in a parallel circuit, we're going to follow this line. That's this blue line. Okay? This blue line goes that way. All right? So, does it really do that? And I've never been able to test this before because I've never had a roller inductor that we could just kind of move around there. So let's get our little VNA out, and let's change the sweep to stop at 3 megahertz. So we're sweeping between 50 kilohertz and 3 megahertz. And we zoomed in all the way here. And we have an open right now, so it's over here. We had a short, it would be over here. So let's add a 50 ohm load. So this is the 50 ohm load that I built the other day. And we're going to put it on our machine. And we're going to check, make sure we're in the center. We are. And now we have some clip leads coming off the T. So these clip leads are in parallel to our 50 ohm resistor. So let's take our roller inductor, okay, and let's connect some things up. Alright, so let's see, how do we want to do this? So you can see everything. I think this might work. No, it's not going to work. Let's see here. Let me flip this around over here, and we'll put the little Nano V over here. All right. Can we see all of that? Yeah. All right. So let's turn off the yellow trace. Oh, it's upside down. Great. Back. Display, trace, off. Alright, so we were looking just at the Smith chart now. So I'm going to start winding on inductance. And it's upside down. It's upside down, it's upside down, it's upside down. Alright, there we go. Alright. Okay. So I started here. Let me turn off the room light so we can see better, our display better. Of course, now we've got room light from the garage door. I don't think that's much better. I don't think that's much better, so I'll turn the room lights back on to get the exposure right. And yeah, let me just kind of hold it here. I think that's going to be better. And then let me start winding on inductance. And you can see that we're going in the up direction, sweeping between basically 50 kilohertz and 3 megahertz, so it's going to be this little short line. And you can see that there's no lines on this Smith chart like I described. There's no blue lines, there's only red lines. But you can see that it's kind of following an arc, like I drew in black ink on that Smith chart. So the more inductance we go, it follows that arc. So let's see. Here's all that inductor will do. So it takes us way over to that side, and it's a bit noisy, so you get those funny little things in between. There we go. So let's go Let's go halfway. All right, so I think you get the idea that we are indeed following this line that I showed you. Okay, so so that was fun. So it does theory actually works? Yay! All right, so now we have our inductor, and what about capacitors? All right, so I said the capacitors go in the minus direction, so they're going to go down, and they're going to follow the same circle. So they're going to go this way. They're going to come down that away. Okay, this circle is a line of constant impedance. So it's 50 ohms everywhere along that, but it has some plus Z in this direction, it has some minus Z in this direction, but its real part stays at 50 ohms. All right, so let's get out our inductor. Here's our inductor, and let's hook up a ground, and let's hook up a plus. All right, so that's hooked up there. And how are we doing over here? Let's take this off, and I think we're kind of, yeah, there we go. I can't see it. All right, there we go. So I'm going to have to hold this on. So we'll start with it open, so no capacitance, and we'll put our ground connection on. There we go. And we're here kind of in the middle, 50 ohms. And now I'm going to start adding capacitance. And yes, it follows that curved line. And that's up to 1500 picofarads, so that's about halfway. Yeah. So that's really cool. So you can see that you can travel different directions. And by having two of them, one that goes positive, one that goes negative, you can kind of travel kind of where you want to go. But it doesn't really quite get you there. You need to have, you need to be able to move in sort of different directions. I showed you that this was an inductor in parallel and this was a capacitor in parallel. If we have it in series, then our capacitor is going to move along this circle, and our capacitor, our inductor goes in that direction, and our capacitor goes in this direction, right? So by having the ability to travel in different directions, you could say, okay, if I'm here and I want to be at 50 ohms, that's what an antenna matcher does, then we need to pick a path. We could pick this path. We could pick a path that goes along this circle, okay, which is an inductor in series. So that's an inductor in series. And then we can go this direction, which is a capacitor in parallel. And that would send us in this direction. So inductance and capacitance would lead us down to our 50 ohms. So that's how an L network works. You could go the opposite direction. You could have a capacitor in series and an inductor in parallel, and get there this direction. So it doesn't really matter if you go that way or you go that way. You still end up in the middle. So you could have an L network where the inductor is on the ground side or the inductor is in series. It works either way. And T networks just add a little more complexity to that. Pi also adds complexity to that. It lets you go different directions and match the input and the output both at the same time. But here's the idea that I wanted you to get, that you travel these curves, and it actually does travel the curve on the Smith chart with real devices. Pretty fun.